All right, so if you've ever found yourself staring at some super dense lecture notes about internet security and just feeling completely lost, you're definitely in the right place. Today, we're going to decode one of the most important moments in that whole process, the TLS handshake. And we're going to zero in on the server hello message. This is that critical moment a website answers your browser to get a secure connection going. I promise, by the end of this, it's all going to make perfect sense. It's something we just take for granted, right? I mean, think about it. How does your browser actually know it can trust a website with your password or your credit card number? How do two computers, maybe thousands of miles apart, cook up a secret code in the blink of an eye while the entire internet is potentially listening in? Well, that's exactly what we're going to unpack.
Believe it or not, it all starts with what's basically a secret handshake. Yeah, I'm serious. The whole process is called the TLS handshake, and the best way to get it is to picture two secret agents meeting for the first time. They have this really precise sequence of signals and countersignals to prove who they are and agree on a secret code before they exchange any actual intelligence. And we're going to stick with that analogy to make all the techie stuff feel a lot less intimidating.
So, the formal name for this whole process is Transport Layer Security, or TLS for short. You've seen it a million times. It's the little padlock in your browser's address bar. And the big idea here, the most important thing to get, is that before a single byte of your data is sent, the client, that's your browser, and the server, the website, they absolutely have to agree on the rules for their secret conversation. So, how does it start? Well, your browser kicks things off. It sends out a message called the client hello. You can think of this like a menu of options. It's your browser saying, hey there, I want to talk securely. Here are all the different secret codes I know how to use, and here are the versions of the protocol I support. Now, the server gets that message, which brings us to its reply. And this is the part your professor's notes are really focused on, and for a very good reason. The ball is now in the server's court, and its response, the server hello, is what's going to decide, well, everything about the security for this whole conversation. So that reply is called the server hello. And here's the key thing to remember. This isn't a back and forth negotiation, it's a decision. The server takes one look at that menu your browser offered, and it makes the final call. It picks one way to do things, and that choice is binding. This one message basically sets the rules for the rest of the game. Okay, so let's look inside the server's message. Right. So if you're studying for an exam, this is where you really need to pay attention. We're about to pop the hood on this message and break down all the technical bits and pieces, using those lecture notes as our roadmap. Okay, take a look at this. What you're seeing is a real-life server hello message pulled from what's called a packet capture. This is the raw data, exactly the kind of thing your professor showed you. Now, I know it looks like a wall of text and numbers, maybe a little intimidating, but don't worry. Just think of it as the server's secret reply. We're going to dive in and decode this thing line by line.
First up is the field labeled server random. You can see it right there, that long string of what looks like just total gibberish. But that isn't just random noise, not at all. It's an absolutely critical piece of the security puzzle. So what exactly is it?
So the technical term here is server random. And just like your notes say, it's a 32-byte random number. Its job is to be what's called a nonce, which is just a fancy way of saying number used once. And that name tells you everything you need to know. It's a totally unique value cooked up just for this one conversation. It will never, ever be used again. Let's go back to our secret agents. The server random is like the unique one-time use password for this specific meeting. And why does that matter so much? Well, it stops something called a replay attack. It means a bad guy can't just record this whole conversation today and then try to replay it tomorrow to pretend to be you. It won't work because tomorrow the server's going to be expecting a completely new and different random number. Pretty clever, right? Okay, so we've got a unique fingerprint for our conversation with that random number. The next piece of the puzzle is this cipher suite. This is where the server lays down the law and decides exactly how they're going to encrypt everything from here on out. Think of the cipher suite as the server's final choice for the encryption recipe. It's a whole package of different algorithms that work together. Now, if you look at the example from the notes, that whole TLS AES 128 GCM SHA-256 thing, I know it looks like alphabet soup, but it's super specific. It's telling both sides, okay, we're going to use AES 128 GCM to scramble the data, and we're going to use SHA-256 to make sure nobody messes with it in transit. It's the exact tool set for the specific mission. And to bring it back to our secret agents, if the handshake was just them agreeing to talk, this cipher suite is the exact secret codebook they've just pulled off the shelf to use. From this moment on, there's zero confusion. Both agents know precisely how to scramble their messages and how to unscramble the ones they receive. Okay, one last critical piece inside this message. It's an extension called key share, and this is the final ingredient we need to actually create the master secret key for the entire session. So what is a key share? Well, it contains the server's public key information. A public key is just a piece of the puzzle that's totally safe to share with anyone. It's public. And as you can see from the notes, it even specifies the exact type of math they're going to use. In this case, a really fast and secure method called x25519. This is the server's half of the raw material needed to generate that final secret. Okay, and this is where things get really, really cool. This is the magic of what we call public key cryptography. The server literally sends its public puzzle piece, its public half, right out in the open for anyone to see. Your browser, meanwhile, has been holding on to its own secret half. And here's the brilliant part. Your browser can take its own secret half and mix it with the server's public half and create a brand new shared secret key. And that brings us to the grand finale of this whole digital handshake. All of those pieces we just talked about, the random number, the chosen codebook, and that public puzzle piece, they all come together for one purpose: to forge the final shared secret key. So let's walk through it one more time. Your browser grabs that public key share from the server's message we just decoded. It then combines that with its own private key that it never shares. Now, at the very same time, the server's doing something similar. It takes your browser's public key, which it got way back in the first message, and mixes it with its own private key. And through the power of some really clever math, they both end up with the exact same secret key. And the most incredible part? They did it without ever actually sending that secret key across the internet. It's amazing. And this, right here, is the moment of truth. Just like it says in your notes, once that ServerHello is sent and received, both sides have everything they need. The secret key is born, and from this point on, every single thing they say to each other is completely encrypted. The handshake is done, the conversation goes dark. Okay, let's pull all of this together. If you've got an exam coming up, think of this next part as your ultimate cheat sheet. This is the stuff that lecturer was really trying to hammer home. All right, here's what you absolutely must remember. First, the ServerHello is the server's final word. It's the decision, not a suggestion. Second, that server random, its whole job is to prevent replay attacks by making every session unique. Third, the cipher suite, that's the agreed-on recipe for all the encryption. And finally, the key share is the server's piece of the puzzle that lets both sides create that shared secret. Put it all together, and what do you get? A shared secret key that protects all the data that follows. And that brings us to one last question to really make you think, to make sure you've got this down. We've talked a lot about how crucial that server random number is, but what if it wasn't random? What could a hacker do if they could figure out or even predict what that number was going to be ahead of time? What doors would that open? Something to chew on. Thanks for sticking with me on this one.